first of all, I just want to kind of dwell on the word sustainability, because it's been around quite a long time now, and as we all know in this media-fired age, terms and concepts don't have a very long shelf life. My kind of personal view, my heartfelt view, is that sustainability is more important now than it was when the term was introduced 10 years ago. And I don't intend to kind of shower you with figures, because figures are for the brain. I prefer to deal in visual images. And this one here, I can only describe, it has an awful bleak beauty to it. It's the largest carbon producer in North America. And ironically, this is the tar sands in Alberta. And we're producing, making the largest carbon footprint in order to harvest fuel which can then produce more carbon. Such is the desperate plight that we find ourselves in. And this in terms of fuel and energy. And there's a similar image which also belongs to North America. Haven't got it in for America, but there we go. And this is in Tucson, Arizona, and reputedly the largest hole in the world, in case you ever wondered where that was. And this is a copper mine, copper and one or two other ores. And the daunting kind of image is that 1 million tons every 24 hours is mined from this big hole. And of the ore that's mined, of the spoil that's mined, less than 0.01% is actually usable metal. And it's 600 meters deep at the moment. I mean, it's absolutely colossal. And for me, it just kind of gives this kind of picture in both kind of a headway and a heartway of the plight that we're actually in on planet Earth at the moment. That's my little tirade on sustainability. And if you don't kind of think it with your head or feel it with your heart, you're going to have to do it anyway, because legislation is now underway when we all are going to be working for zero carbon buildings. You won't have the likes of us up here swanking about having one, because all buildings will be zero carbon. Oh, I didn't know I got little pop-ups. Okay, sorry. (2018). This series of slides belongs really to Alan, who's going to talk a little bit later on servicing. But I do like this little kind of gambit of the lean, mean, and green, because as a designer of sustainable buildings, it absolutely encapsulates what we're trying to do. Lean in terms of a passive approach, embodying in the form, in the context of the building, sustainable principles. And I'm not going to just read bullet points. And it's at this stage when the die is cast, so to speak, that once one has the conceptual kind of form and figure of the building, there's really very little that one can do other than make it more efficient, which is fine, and we can just run through the bullet points for efficiency. And lastly, to make it green, which is all the green add-ons, be it solar water heating, PVs, and the like. Important, but not really fundamental to the design process. I I'd just like to linger and kind of share this thought with you. And I'm speaking more now as a structural engineer, that we're at a kind of crossroads. On the one hand, we have traditional construction, where we're using a lot of low embodied material, quite often in a kind of a craft way. It gives a low tolerance manifestation. We also find ourselves in an industrial age, and in the building industry, we're unbelievably slow at coming to terms with this, in terms of lightweight construction, in terms of small quantities of quite what often is a high embodied energy material, for instance, aluminium. And these are some images which I like to show. If you were a reasonably wealthy punter back in the 1930s, this could be your choice of limousine. And you'll notice one limousine really stands out above all others, and it's the Chrysler Airflow on the top. Absolutely seminal piece of structural design. It's one of the first, if not the first time that we use stress skin monocoque construction. And I'd just like to kind of dwell on this thought, if I may, and what I'm trying to do here is, where does sustainability meet structural engineering? It meets it in trying to reduce the amount of material and embodied energy that we're using. And this is a fantastic slide. If you go to York Railway Museum, it's still there, and one can compare the old post and frame tradition with the stress skin tradition. And we've been trying to use stress skin structures, and bridges is one that did kind of recently, of trying to do this more with less. But for some reason, the building industry is inherently conservative in this country, probably more conservative than in most other European countries. And one last thought that I'd like to leave you with is this relationship between skin and structure. And what we found, we're working with Andrew Yates on the largest passive house housing scheme in the UK, is this incredible air tightness requirement, 3 or 4 times more severe than what we've been used to. And this poses some very interesting questions for the design team, for the structural engineer, in terms of whether the structure is what I would call endoskeletal, inside the skin, exoskeletal, outside of the skin, or actually a part of the skin, as in stress skin construction. And as usual, kind of nature has its own wonderful message to show us. And just lastly, because my minutes are almost up, and this is really coming into a more kind of architectural context. I suppose I'm very much a modernist, and I like to see structure exposed. But as soon as we expose structure, we pierce the skin. And one of the points that Peter will raise on Harlow Carr is that we had to come to terms with this halfway through the design, that our skin was being punctured. And this is a school that we completed 3 years ago, or 2.5 years ago, with Marks Barfield, Michael Tippett's school in South London. And I mean, it is a sustainable building, it's naturally ventilated, but we wanted to express the structure. And what I see is a new era of form starting to take place where the skin is dominant. It's very, very rarely now that one sees exposed structure. And on that note, I'll hand over, and Peter will home in actually on Harlow Carr itself.
Okay, thank you. Yes, what I'm going to try and do over the next 10 minutes or so is try and show how at the building in Harlow Carr, the Bramall Learning Centre, how we managed to apply, or how we tried to apply some of those principles which David talked about in the first 10 minutes. Our client was the Royal Horticultural Society, and these are the gardens of Harlow Carr, which are just outside of Harrogate, and it's kind of their northern headquarters. And what they wanted was a new learning centre to be built in these beautiful gardens, and there was a very clear desire right from the very outset that this building would be one of the most sustainable buildings around. There's our building just by the main entrance, and on the hill opposite you will see later where we put the wind turbine to power the building. So a close-up view of the site now. The most important feature about the site is that it's sloping. It's sloping east to west, which meant that our building was partially earth-burned. Because of this east-west slope, and the orientation of our building was actually in north-south direction. And we wanted to maximise the amount of southern elevation, and from there we got this S-shaped building plan to maximise the amount of southern elevation available to us. At the very heart of the building was the servicing strategy. Here we've got the west and the southern elevations at the double height, and then the back of the building is the single height. It's partially earth-burned rear retaining wall, which meant the building was single height as you approached it from the road. The glazed front elevation draws the heat and the natural daylight into the building, and then the building structure itself acts as thermal mass and emits, in effect, coof into the space. And there's actuated louvers within the facade, which then help to cool the building down overnight, ready for the next day. In concept, the building consists of kind of three major components. Number one, we have this kind of reinforced concrete bookend, which is embedded into the hillside. We've got a reinforced concrete table structure, and the roof structure is this kind of timber hat on top, to reduce the amount of carbon embodied in that structure. All the concrete was specified to have 50% cement replacement, and we used granulated blast furnace slag, which, for those of you who don't know, is the byproduct of the coal-fired power stations. And all the timber was FSC certified with full chain of custody certification. The backfill to the retaining wall, we found a local reinforced, local recycled aggregate supplier to reduce the amount of virgin aggregate used in the structure and the civil works. The building has been calculated to be carbon negative, and this is achieved in part by the 20-metre high, 15 kilowatt wind turbine inserted on the hill opposite, 100-metre deep ground source heat pumps, and an array of solar thermal panels for domestic hot water on the southern parts of the roof, southern facing parts of the roof. And through this, on your right-hand side, we've reduced the electricity demand of the building, and when the wind turbine's going, it produces more electricity than the building actually uses, and any excess electricity is then fed back into the grid. I should say we just recently secured funding to do a post-occupancy evaluation of the building to see whether our calculations hold true. Now into the building materials. All the partitions within the building are either unfired clay brick partitions, or where we have concrete blocks in the external cavity walling, we've replaced the aggregate with 100% recycled aggregate is in that blockwork. The retaining walls around the building are made up of gabion walling, and the stone is sourced locally. We have an underfloor heating matrix on both floors, and this is embedded in an eco-screed, which the aggregate part of that screed is made up of recycled glass, and the binder is a desulfurized gypsum, again from the coal-fired power stations. A little bit on the external cavity wall. We've got 250 millimeters cavity within that wall, and that's fully filled with insulation. And what we found was when you increase the insulation to those sort of levels, that the actual ties through the insulation become quite significant in terms of their cold bridging. And so we used these wall ties, which are made from basalt fibre, not only to reduce the cold bridging effect, but basalt is a far more abundantly available resource than steel is for the equivalent wall tie. Our U values were far higher than what the regulations required, approaching that of passive house standards. And so any structure which penetrated the insulation had to be thermally broken, and we had to develop up specific cold bridging details. This one was with shirk, and this is the connection between the first floor slab and the retaining wall, which the cold retaining wall and the warm first floor slab along the back of the building. And there's the retaining wall going up. Just a few slides of the building being constructed here. You see the roof structure being built. Onto the roof structure. The primary structure was formed with these S-shaped twin glulam beams, and these with softwood sawn purlins between. This was sheathed with a plywood diaphragm. Because the insulation was on top of the roof structure to reduce the cold bridging effect of the structure, that meant that all the structure was on show. And we had to develop up these bespoke connection details where we have steel plates flitched into the end grain of the timber, and rather than having traditional bolts with large heads and nuts, we have steel dowels which are rammed into tight tolerance holes to give a far more pleasing aesthetic to the roof structure. And the main column beam connections were these expressed pinned connections, again specially made for this project. Onto the roof diaphragm. I think this relates back to what David was talking about with the structural skin. We had a kind of asymmetric arrangement of brace bays, and in order to get the wind which was blowing on the facade distributed out into those brace bays, we needed this plywood sheathing to act as a stiff diaphragm. Our initial calculations showed we needed something in the order of 25 millimeters of plywood to do this, and because it was curved, these had to be made up with laminates no thicker than 9 millimeters. In an ideal world, we would have made these off-site and laminated them with the required profile, but cost and logistic constraints didn't allow this, and so we had to laminate these plywood sheets on site. We would have liked to have used glue, but because of the quality control on site doesn't always allow that. We had to develop a mechanical fixing detail to accommodate this, and the entire roof structure was explicitly modelled in a very detailed finite element model, which allowed us to predict different densities of mechanical fixings across the roof diaphragm, depending on how hard the diaphragm was working in that particular location. And it went up pretty quickly in the end. They developed special templates that they could just zip around with the powered with the power screwdriver, and it went up pretty quickly. And the end result, we were very, very pleased that all the hard work we'd put into this roof structure had paid off with quite a beautiful roof. I think I'm running out of time, so I won't read out all of these, but this BREEAM rating refers back to the client's aspiration to have one of the most sustainable buildings around, and at one point during the design process we were scoring the highest scores ever been recorded by the BRE, and in the end I think after a couple of rounds of value engineering we came back to about number 3 in the country rankings, but still a fairly high BREEAM rating. And there's the U values for the record. Yeah, just on the BREEAM rating, it was quite interesting. The two places where we lost quite a lot of points was under the energy and transport category, because we weren't on a major bit of rail infrastructure or anything like that. We couldn't achieve those points, and also in the land use and ecology, the fact that we started with a greenfield site meant we lost out on points there. A little bit on costs, because we'd all love to have buildings like this, but can we afford them? The headline figure, if the kind of notional comparable building might be about £2,100 per square metre. Ours was £2,800 a square metre. Of that difference, half can be attributed to the building form and the location, and the other half down to the sustainability features. So perhaps not as expensive as you might have thought. A little bit on awards. We've won many awards, including the Institute of Structural Engineers and the RIBA, but perhaps the one we're most pleased about is the Sustainability Awards by the UK Green Building Council, where we were the Sustainability Project of the Year last year. Thank you very much.